My name is Kevin and I'm a final year PhD student here at the University of Melbourne, and today I'll be talking about some of the problems we currently face in predicting turbulent rough-wall heat transfer. So my talk is going to be in two parts. The first, I'm going to cover the fully rough regime for heat transfer, and the second is going to cover transitionally rough regimes, where I'll look to populate this outline as we move on in the talk. And so I'm interested in predicting rough-wall heat transfer, where for any given situation, say, I could identify a roughness size K on my surface, and I might be interested in predicting a heat transfer coefficient for this situation. And so if I have some mean temperature theta with respect to wall normal distance Z, what I can infer from this profile is a bulk measure or a heat transfer coefficient, say the Prandtl number St, or alternatively, and what I'll be using this talk is the heat transfer augmentation relative to a smooth surface, delta theta plus, which is going to depend on my roughness size K, as well as the Prandtl number, which is a property of the working fluid. But here I'll highlight the issue we currently face in predicting delta theta plus, where I'll use a single working fluid or Prandtl number of 1 to illustrate my point, and I'll plot this against Ks plus, the equivalent sand grain roughness, which for those unfamiliar with the roughness literature, you can think of as going from smooth to rough. So amongst many popular software, textbooks, and the literature, what we'll find is a diverse set of predictions. And even if we had access to some high fidelity recent DNS from Peters and Sandom, say, I show here, we still don't know what is really the right answer. And actually, what I want to highlight now is that we've had access to mean data, high quality mean data for quite some time in the form of the experiments of Diprey and Sibirski, and all the models I actually show you are tuned to the original data set of Diprey and Sibirski, where at the time they plotted their data in this so-called G function, which is related to delta theta plus up top. And typically, fully rough regime projections take the form of a scaling law for this G function, where the Diprey and Sibirski proposal at the time was empirical, but since then there have been a number of analytical proposals that have emerged. Here I'll highlight the quarter power scaling of Broussard and the half power scaling of Owen and Thompson and Yaghlom and Kader, and the correct value to take for this exponent has been an ongoing topic of debate, as elaborated in both Li et al. And Chang et al. But the key takeaway I'd sort of emphasize here is that inspection of mean data alone is unlikely to reveal to us the truth, and what we need instead a bunch of high fidelity data in this high Ks plus regime so that we can start probing some of the underlying flow physics. And so in order to reach these high Ks plus regimes through DNS, we'll be adopting a minimal channel approach whereby we truncate the size of our channel domain while still accurately resolving the near-wall roughness sublayer flow up to some critical height ZC. So here I'll be considering a 3D sinusoidal roughness and systematically varying the roughness Reynolds number K plus and the Prandtl number. And I'll be normalizing quantities on the global friction velocity U tau, which is defined on our total wall shear stress tau W, and friction temperature theta tau defined on the total wall heat flux QW. And so enabled through our minimal channel approach, what this gives us is access now to high K plus data in the fully rough regime, but also higher Prandtl number data, which for a conventional DNS would be very difficult or impossible to simulate currently, owing to the very small scales that need to be resolved in these simulations. And to contextualize what we've gained, here I'll just isolate the Prandtl number 1 simulations we have, and go back to that delta theta plus plot for Prandtl number 1 I showed earlier. And if I now overlay our present data, you'll see now we've extended the coverage in the high Ks plus region, where Ks plus is proportional to K plus, which I've attained by considering the analogous momentum problem for delta U plus, and which I won't have time to cover today, but for the time being, you can just think of Ks plus as being proportional to K plus, such that their scaling behaviors can be considered interchangeable. So now with the comprehensive data at our disposal, let's go ahead and examine our mean flow data first. Here I'm showing the original G function plot of Diprey and Sibirski. And what I'm just going to do first is trace their data onto a new set of axes. And now what I'll do is I'll overlay our present data also alongside the data of McDonald et al., who considered the same 3D sinusoidal roughness as us. And here amongst our data, what we obtain is a similar scaling behavior to Diprey and Sibirski, namely a scaling which more closely favors the quarter power scaling of Broussard as opposed to the half power of Owen and Thompson and Yaghlom and Kader. And if we're to unpack the full scaling laws of these authors, where now I include the Prandtl number scaling that was proposed, what we find empirically is that much like Diprey and Sibirski, our mean data again favors the exponents of Broussard, with a Ks plus exponent of about 0.2 and Prandtl number exponent 0.4. And so from this, we might be tempted to conclude that it's a done deal. The Ks plus to the half exponent is clearly not appropriate for describing fully rough heat transfer. But what I'm going to demonstrate now is how the Ks plus to the half exponent can actually provide a valid prediction when we examine the flow locally. So here on the right, I'm showing the same g function plot previously, and what I want to do now is unpack its definition and highlight in particular that it provides a measure of the mean average heat transfer across the surface QW, which I'm emphasizing with these angle brackets. But evidently, we might expect to find different scaling behaviors depending on where we might look. Here, for instance, if I isolate a peak region where the wall might be exposed to a relatively higher shear, and in fact, the idea of both Owen and Thompson and Yaglom and Kader was that we could envisage the rough walls locally as being analogous to a smooth wall flow, such that we can rely on what's known as Reynolds-Chilton-Colborne analogy prediction for the heat transfer, given by the Stanton number, or just Reynolds analogy for short, which we'll find widely used amongst many textbooks. So at the time, both Owen and Thompson and Yaglom and Kader proposed that such a scaling could describe heat transfer across the entirety of the rough surface, which we now know to be incorrect. But here, what we'll propose and return to is to consider only the heat transfer locally at an exposed region, say the roughness peaks, exposed to high mean shear, and where we might expect the flow to be most analogous to a smooth wall. And so now, if I consider the same quantity as I had above for the g function, only this time I consider the heat transfer averaged only over my peak regions, which I can interpret as essentially being like a local g function at my peaks. What we can now see is a behavior now beginning to more closely favor the predictions of Owen and Thompson and Yaglom and Kader for Ks plus to the half, as opposed to the quarter power for the global heat transfer. And moreover, a Prandtl number exponent m that is also beginning to resemble the 2/3 that we'd expect for a Reynolds analogy type prediction. So much of this now prompts questions regarding the validity of Reynolds analogy for rough walls. And so conventionally, it's been widely understood that owing to the addition of pressure drag, this causes a breakdown of Reynolds analogy such that the wall shear stress and heat flux are no longer correlated. And this has been a widely accepted conclusion time and time again amongst many authors. But here, what I'll show is that we can in fact recover a Reynolds analogy type behavior locally, where instead we consider only the local viscous stress component of the wall shear stress tau nu. And to examine this, I'll be plotting joint PDS between the viscous stress and wall heat flux, normalized on their respective mean values across all my Prandtl numbers in the fully rough regime. So first, showing when I sample across the entirety of my rough surface, we can see some semblance of correlation persisting between the viscous stress and heat transfer, but this is very much weaker than what we see in a smooth wall flow, which I show here, where the correlation between the viscous stress and heat flux remains strong. But now, in line with what I showed previously, if I now conditionally sample my regions locally to my roughness peaks, I'm now starting to recover a more smooth wall-like behavior, or in other words, towards a Reynolds analogy type heat transfer. And so the key takeaways in the first part of my talk are that although we might find a Diprian-Szyberski or Broussard-like behavior in our mean heat transfer, locally in fact we can recover a Reynolds analogy type behavior in exposed regions, which runs contrary to how we might view a rough wall heat transfer conventionally. And so for the second part of my talk, I'm going to demonstrate how we can use virtual origins to model transitionally rough heat transfer. So if we go back to our delta theta plus plot we had earlier, what I'll be considering now is this lower Ks plus region. And in particular, I'm going to look to apply a Lucchini 1996 framework to model this regime, where delta theta plus is going to be determined based on these two virtual origins, L theta and D, which I'll explain shortly. So returning to my parameter space, what I'm going to consider are my low K plus regimes here at this K plus equals 6, and what I'm going to do is I'm going to zoom into my flow very close to the roughness, and I'm also going to consider my time average flow now. And so conventionally, the way we understand these types of flows for very small roughness is that they're sort of analogous to an otherwise smooth wall, relative to some reference plane that we need to determine. And in fact, this was the idea of Lucchini 1996, where he proposed that the drag delta U plus could be determined based on a virtual origin perceived by the mean velocity Lu, and then also a turbulence origin D. And in the context of drag, this idea has been explored by a number of authors, some of which I show here. But today, what I'll be showing is how this drag prediction of Lucchini can be generalized to predict heat transfer here in the form of delta theta plus. And so this prediction hinges on two quantities, both of which we can calculate empirically. The first of which is the virtual origin perceived by the mean temperature, L theta, which we can attain by shifting our mean flow origin to match that of a smooth wall mean flow. And the second of which is the turbulence origin D, which we can obtain by shifting our Reynolds shear stresses to match that of a smooth wall. And here we have assumed that the origin perceived by the heat transfer is inferred from the momentum field through the Reynolds shear stress, such that the D you see here is identical to the D in Lucchini's prediction for the drag delta U plus. And so now let's go ahead and test this prediction. Here I'm showing smooth wall data first for our present Prandtl numbers. And now if I plot our rough wall data measured from my mean roughness height Z plus, where here I'm only showing data above my roughness, we see that now if I plot my rough wall profiles relative to their turbulence origin D, this enables me to first match the slopes of my profiles with the smooth walls, and now I can apply the shift I'm predicting for delta theta plus based on my virtual origins that I'm showing up above. So here we can see that doing so allows us to collapse all our lower Prandtl number profiles with the smooth walls, and here we also see that the prediction is not so good for a high Prandtl number case of 2. And this perhaps could have been anticipated from the near wall flow we visualized previously, where at our higher Prandtl number of 2, the roughness elements appear to be perturbing the near wall temperature more significantly than the lower Prandtl number counterparts, such that the smooth wall-like structure at high Prandtl numbers is less evident. And so to conclude the final part of this talk, what we've demonstrated is that a virtual origin framework of Lucchini can provide a valid avenue to model transitionally rough heat transfer problems. And just at the end, I'd like to acknowledge the helpful discussions of both Detlef and also Jeremy in preparing this work. And with that, this ends my talk.